So we're going to introduce today logarithms. Now you've seen this before, assuming in Algebra 2 trig, so we're going to go through it kind of quickly, but we want to start with an overview of what logarithms are. And so we have this question of what are they? They look really weird in terms of how they're shaped, how they're expressed, but they kind of make sense if we think about it as an inverse. So if I take a value x and I have an exponential, so a times b to the x power, I get some exponential function. And that gives me a value, f of x. Now if I want to go the other way, I need an inverse. So I take the function, I get back to x. That is our logarithm. So it's an inverse of our exponential function. So it undoes the exponents. It has to deal with exponents. So any property that we have for exponents, we're going to have for logarithms as well. So let's look at some examples. If I have x and I raise it, that's my function, exponential function, I get some value. If x is 2, I plug in a 2 for that, and I get 300. Now if I want to get from the 300 back to 2, what do I need to do? Well, we have a method that gives us our inverse, right? We take our general function, and I switch the x and y values, and then I solve for y. Now remember, the inverse takes an xy pair, so if I have the point 2, 300, it's going to give me 302, so it swaps the ordered pair. That's where the switching of the x and y come from. So let's do that. So my function now looks like this, where I switch those two, and I get x equals 3 times 10 to the y. Now, I can see that I divide by 3, and now I'm kind of stuck. I have this y in the exponent that I need to bring down. I need to get it out of the exponent spot, and that is where our logarithms come in. So how do we do that? Well, we're going to define something called a logarithm. So if I have this expression, log base b a of a, not times a, but of a equals c, what this says, the way we read this, is c is the power I raise b to and get a. So we're looking at a power. So if I take that expression and use it for what we have over here, what this is going to look like is log base 10 of x over 3 is log base 10 of y. And now, while it looks confusing, it's actually become simpler because log base 10 of y is y. Because what that's asking is, what's the power that I raise 10 to and get 10 to the y power? Well, that power is y. So I've solved for my expression, and so the inverse is this thing called the logarithm. So we'll look at some examples as we go through this. Alright, just to make sure we understand, what is this going to equal? Now it looks really scary, right? We have this 3 raised to some power. Now we notice that we have a 3 down here as our base, right? And then we have this expression. This is going to be actually pretty simple, because if I look through it, what this is telling us to do is, what does this mean, right? 3 raised to the log base 3 of 1.5. Well, log base 3 of 1.5 is something, and that something means something is the power I raise 3 to, and then I get 1.5. Well, what we've done is we've raised 3 to that power. Now, the logarithm isn't a nice number, however, but when we raise 3 to that power, I know I get 1.5. So if I just substitute in the question mark for log base 3, 1.5, we get that there, which equals 1.5. And the last step is to multiply it all by 4, and we get 6. So the whole expression is 6. So again, things can look complicated and scary, but we just have to read them and make sure we know what's going on. Alright, so this is our general expression, right? And we want to read this as x is a power. So logarithms equal a power. That's the power I raise b to, and I get y. And what's going to happen is my properties of exponents are going to work as my properties of logarithms. So if I have log of x times y, that's log base b of x plus log base b of y. Why is that true? Well, let's look at an example, right? 10 to the 6 times 10 squared, that's 10 to the 8th. We add the exponents there. Well, if I was to look at logarithms, right? Log base 10 of 10 to the 8th is 8. That's the power I raise 10 to and get 10 to the 8th power. This one is going to be 6 plus 2. So we can see that that is equivalent to log base 10 of 10 to the 6 plus log base 10 of 10 squared, which gives us our expression at the top. Now we could do the other ones as similar analysis, but I'm going to save us the time for maybe down the road. The ones that we're going to use the most are powers of logs, and then the change of base, and we'll see why change of base is important it's going to be important for solving exponentials because on our calculator we only have two bases that are allowed. One is base 10, which makes sense for our number system, and the other is something called base e, or the natural logarithm, which we'll see why that's important in a little bit. Alright, so we want to simplify these using those powers that we had on the other side. So for the first one, I'm going to bring down that 3. There's my power law. And now I have division and multiplication. So the division means a subtraction of the logarithms. And then I see on the term that's right here, I now have multiplication, and I'm further going to have a power law where I can take these exponents and I can bring them down in front. So we just expand what we have. There's my addition, and then I brought down, from here, the 2 comes down in front of the logarithm there. I'm going to be able to do the same thing with this 3 and bring it down in front of the log base 4. Alright, so there's my expression. Now since I have x, y, and z, there's nothing that I can evaluate. If I had powers of 4, we could go further than that. Alright, for the next one, I'm looking at going the other way around. I want to rewrite it as a single logarithm. So anytime I have a multiplication of a number or an expression in front of a logarithm, I can bring it up to the power. So you can see here I have this 2, and it'll come up and be my power. 3 comes up and be my power there. So I rewrite it like that. And now I notice that I have subtraction between my two logarithms, and I have addition, which means the subtraction is going to translate into division, the addition is going to translate into multiplication. And again, one thing that I haven't said much here is they're all log base A, which means I can bring them together. It has to have the same base. Log base A, log base B are not going to combine like this. Now, since I have addition between the two, that translates into multiplication. So I get log base A x squared times z over y to the third. Now we can use these to help us write and solve things with logs in them as writing it as an exponential. So if I take this one over here and combine them. Now again, I brought the log base 2 to one side and I brought the 3 to the other side. And now that I have subtraction between the logarithms, that means division. So I bring them together like that. And now I'm a little bit stuck, but if I think about what I need to do, I can raise 2 to that power. Now while it looks more confusing, log base 2 of that power equals, right? 2 to that power is x squared over 2. 2 to the third is 8. Multiply by 2, x squared is 16. X is plus or minus 4. Now if we put a negative in, we'd have to talk about that in terms of our domain. But let's leave it be for now, and we'll come back to it at a different point. For my next one, I want to bring them together. I have addition, which means multiplication, and then log base A of 24. 8 of those powers means I get those expressions in there. X squared minus 1 is 25. X squared equals 25. Okay, so now let's talk real quick. So I have algebraically plus or minus 4 and plus or minus 5 as my solutions. However, let's just say we had an easier one where I'm asking for log base 10 of negative 10 equals what? Right? Is there any solution to that? Well, can I raise 10 to a power and get a negative number? And you might think, well, negative exponents. But negative exponents just produce a reciprocal. They don't produce a negative number. So my logarithm is only defined for positive values. I can't turn a positive into a negative by just taking powers of itself. So if I have an x squared, if I look at my expression, if I took the negative 4 and I plug it back in here, I'm going to get negative 8. Well, there's no way to raise 2 to the negative 8 power. 2 to a power and get a negative number out. So my only solution is the positive 4 and the positive 5. I can't have a negative logarithm. All right. So these are why really the change of base can come into play. And this is why we care, because I have a button on my calculator. It's not, more often than not, we're not going to have a nice logarithm to deal with. So if it's not given in base 10, we can change it to it. Or if it's not given in base E as natural log, we can change it to it. So let's see how this works. If I have 5 to the x equals 20, if I take the logarithm of both sides, that's okay because it's the same quantity. And then I can bring down the x in front of the log base 5 with my power log. And now these are expressions I can divide by log 20 over log 5, which equals 4, right? No. We can't, just like sine, cosine, and tangent, it's a function. The log is a function. It's not a variable in front of the 20 and the 5. We can't cancel it. If you do that, you're going to cry real tears. So what you need to do is evaluate both of those numbers on your calculator, all right, and you get about 1.86. You can plug it back in and try. We know that makes sense. If I think about it, 5 to the 4th power is not 20. 5 squared is already 25, so it's got to be bigger than 1 and less than 2, and 1.86 works that way. So let's look at the next one. I take the log on both sides, right, and I get log to the 7 to the 3x. Log 5, bring those x's down in front, and I divide both sides by by the x, and I get 3 is log 5 over log 7, but 3 is not equal to 0.82, so what happened here? When I divided by my x, there's only one number I can't divide by, which is 0. So if the solution is x is 0, I had an illegal operation, so I need to figure out if I really have a solution or not. Well, I plugged through it, right? Let's see, if I subtract it from both sides instead of equal to 0, and then factor out the x, that's my expression. I don't really care what 3 log 7 minus log 5 is. It's just some number. It's not 0, so that means x has to equal 0, which works out if you have, if we just go back to the initial expression, 7 to the 0 power is 1. 5 to the 0 power is 1. And again, we got the problem the first time because we can't divide by 0. Alright, let's look at the next one. Sometimes you can just use the powers. So if you see 8 and you see 4, those are both powers of 2. We can express them as powers of 2 and then just set the exponents equal to each other. We could take log base 2 and bring it down and all that, or take log base of 10 and use our calculator, but we just can set these two equal to each other, and I get x is 8. The next one is a special case of factoring. So if I have a substitution where u is e to the x, I get a quadratic that factors into u minus 2, u minus 1, substitute back in u minus x, set them equal to 0. E to the x is 2, e to the x is 1. If you take a natural logarithm of both of them, the natural log of e is asking for the power you raise e to and get e to the first power. That's 1. So you get x is the natural log of 2. And for the next one, e to what power gives me 1? That has to be 0.